Okay, folks, now that we know a little bit more about waves, let's start the conversation about how we relate the idea of waves to electrons. So it starts way back. This guy named Max Planck did something called the black body radiation experiment. And it was pretty complicated, but I'll simplify it down for you. So I want you guys to think about a piece of metal. Okay, woo, that's really... So a piece of metal that normally doesn't emit light. That's called a black body. Anything that normally doesn't emit light on its own is called a black body. But if you get it really hot, we know that metal, if you get metal really hot, it does eventually begin to glow. And if you pay close attention when you start to heat up a black body, it'll start to glow. First, it'll glow red, okay, as it begins to get hot. And then as it starts to get hotter and hotter, it'll start to grow orange. And then it'll start to glow yellow. And then eventually it will start to glow white. And I will remind you guys that white light is the combination of all colors. If that's something you never learned, you should learn it now, that white light contains all colors of the rainbow: red, orange, yellow, green, and blue, and indigo, and violet. And when they all shine together, that combines and we see white light. So black body radiation is actually emitting every single frequency of light, but it's combining, and so we see it as white hot. Okay, if you guys have ever heard something called white hot, they're referring to that white light being emitted. So what he did as this black body was being heated, he had a prediction. This is what he predicted. He predicted that as he added more heat to the black body, the frequency of light coming off the black body would incrementally increase as well. Okay, so this is what he expected to see. He expected to see low frequencies coming off first and then higher frequencies coming off later. And he expected it to come off like incrementally, gradually, like this in this linear fashion. Okay, however, more interestingly, that is not what happened. Okay, this is wrong. Instead, what he noticed, okay, as he was paying attention to the frequencies of light coming off of this black body, that as he provided more heat, the frequency would jump. Okay, frequency. Okay, the frequency would jump. So the heat source is being studied, but then the frequency would jump in like stair-step ways. So it would stay the same frequency, and then it would jump up to the next one, and then jump up to the next one, and then jump up to the next one. It was this incremental increase in frequencies. Okay, so that means, interestingly, this frequency was shown and this frequency was shown, but the ones in between did not. Okay, and this frequency was shown and this one was shown and this one was not. Okay, so that basically allowed Max Planck to conclude that energy does not travel in a stream, but rather in packets called quanta. Okay, quanta is the plural, quantum is the singular. Of quanta. So what this basically means is that light travels in like these packets, essentially. So how else do I explain this? So if I gave you like a quanta of light energy, it would be like a certain, like you would have, let's say you have 10 joules of light energy, and if I gave you a quanta of 5 joules, you would then have 15 joules of light energy. Okay, he basically, realized that light is not traveling in a stream, it's traveling in these like fixed packets of energy. Okay, so Einstein heard about this whole concept and he was intrigued and decided to do his own experimenting, and he did an experiment that confirmed everything that Max Planck observed. Okay, so this is called the photoelectric effect, and I think I have I do. Okay, so I'll draw it over here first. You guys don't have to copy this one down because this is what was observed, and then I'll have you copy down the thing that actually was happening. So follow with me real quick. I know this kind of sounds a little bit weird, but what I want you guys to imagine is a piece of metal. that has an electric charge on it. Think about like static electricity, like when you zap somebody with your finger after you run your feet over a carpet. So think about that, a piece of metal with like static electricity on it. So you've got some electrons stuck to the surface of this metal, okay, with static electricity. What Einstein realized is that if you shine red light onto metal, okay, we know that red light has a certain amount of energy in it, okay, right? Red light is found on this spectrum, so it does have a certain amount of energy. And so if you shine red light at this piece of metal with electrons stuck to it, nothing happens, okay? And then if you shine green light, green, at this sample, you see a few electrons will jump off, kind of lazily. They'll be slow, and it'll happen occasionally, okay? However, if you shine violet light at electrons, they will all start to fly off enthusiastically. Every single electron is just ejected with lots of energy, okay? And Einstein was really confused by this because like he would make the red light really, really, really bright. So a lot of energy was making its way toward this piece of metal with the electrons on it. And even no matter how bright he made the red, nothing would come off. And then meanwhile, even a really dim violet light would still manage to shoot all these electrons off. Okay, I want to remind you really quick, guys, if we compare red and violet, red is on the low energy side of the spectrum, and then violet is on the higher energy side. Okay, so this is what Einstein realized was happening. Okay, this is what's actually happening, and feel free to pause and copy this down. So Einstein realized that the light that was shining on these electrons was traveling with it in packets. It was like not traveling as a stream of energy, but instead as individual packets of energy. Now imagine that these electrons are stuck to the surface of the metal with like 3 joules of energy. Okay, that's like the energy of attraction. Okay, it's like they're sticking energy. Okay, now if each little packet of red light only carries with it 2 joules of energy, it's not going to be enough to overcome the sticking energy, and the electrons are going to stay stuck to the metal piece. Okay, so no matter how many times I throw a ball that only contains 2 joules of energy, it's not going to overcome 3 joules of energy. Okay, that's why these electrons stayed stuck. Meanwhile here, the 4 joules of energy carried by each green ball of light, okay, did contain enough energy to break that sticking force and then knocked some of the electrons off, okay? Meanwhile, violet contains way more energy, okay, per photon. This is what they're called. Their individual balls of light are called photons. So each little photon of light carried with it 10 joules, and that was enough to unstick the electron from the surface of the metal, and the extra, so 10 minus 3 is 7, so the extra 7 electrons made the electrons, or the extra 7 joules made the electrons fly off with a lot of enthusiasm, okay? So that's what Einstein realized, is basically with this experiment that light is quantized. That means light travels in packets, okay? It travels in little particles, and those little particles are called photons. Okay, so Einstein concluded that only specific frequencies of light could kick off electrons. Kick electrons. This means that different frequencies of light carry different amounts of energy. And Einstein came up with a new term for the quanta of light energy called a photon. Okay, so that is the photoelectric effect. What these two experiments together basically helped us realize is that light travels in energy packets. It does not travel as a consistent long wave of energy, but instead, along that frequency of light, we get packets delivered along the way. Okay, so this is where the paradox of the wave particle paradox of light exists, because we do have proof that light does exist as a wave, but now with these experiments, we also have proof that light can exist as a particle as well. And the even creepier truth is that both are true. light can exist as a wave and as a particle. And it's something that in science, we are still struggling to understand how this happens. Okay, okay, so in terms of how we calculate how much energy is carried by light, there is a formula for that. The formula looks like this. So the energy carried by a particle of light is E equals h nu. E is the energy in joules. H is Planck's constant. This is a number that is going to stay the same every time you use it. It's 6.626 times 10 to the negative 34. This is the Planck's constant that was mentioned in the episode of Stranger Things. I don't know if you watched that show, but it comes up. Okay, and then we know that the symbol is frequency. Measured in hertz or s to the minus 1. Okay, so let's see, let's look at this first question. Oh, guys, by the way, this can be a triangle, right? So let's see, it would be E on top and then H V here. Okay, so there's your triangle to help you figure out how to do the homework. So let's take a look. What is the energy of a wave with a frequency of this? Okay, so if we're solving for the energy, cover-up energy, we get to go Planck's constant times frequency. Okay, so energy equals Planck's constant times the frequency, 1.28 times 10 to the 17 hertz. Okay, make sure you're using parentheses, folks. So we're going to do this number in parentheses times this number in parentheses. And if you crunch that out correctly, you should get 8.48 times 10 to the negative 17 joules. Okay, so there you go. And then the question is, what's the wavelength of the wave in the previous question? That goes back to our previous formula, right? C equals lambda nu. So if we're solving for wavelength, we're going to be doing, let's see, we're going to be doing wavelength equals speed of light divided by frequency. Okay, so the speed of light, we remember 3.0 times 10 to the 8th meters per second in parentheses divided by the frequency mentioned in the previous question, 28 times 10 to the 17th. Hertz. Okay, and we get 2.34 times 10 to the negative 9 meters. Okay, so there you guys have it. Feel free to get started on your homework. Thanks so much for paying attention.